Okay, we're going to start section 3.3 here today. The first two sections in chapter 3 were when we were doing all those steps and we were trying to graph functions by hand. And I know that that process was tedious and it took a lot of room on your paper to be able to do that. We're going to be going in a little bit different direction here today, but still tying in some pieces that we learned from graphing by hand, but we certainly won't have near the amount of work that was involved in those last two sections. So the topic in this section is called optimization. And when you look at the root word of the word optimization, it's the word optimize. Okay? And optimize is basically talking about trying to get the most out of something, usually maximizing something. It could also mean the opposite of that. It could mean to minimize something. And so you can see here on the notes page, it references that to optimize a function, it means we're either trying to find its maximum or its minimum. Now, if you recall, when we did the first derivative sign diagram, we would have, a critical value coming down through here, and then anytime our arrows would sort of be going in this direction, we would always have called that a max, or if the arrows were kind of funneling in this direction, we would call it a min, okay? Now, I do want to distinguish between what an absolute max and min is as compared to a relative max or min. These were typically relative maxes or mins. There were other points that may have been higher than that point on the graph, but it was a maximum in relation to the points that were immediately to its left or right. Okay, what we're going to be looking at here now is we're going to be looking at what's called an absolute maximum or an absolute minimum. Now, if I throw the word absolute in front of that, now we are talking about like the highest point or the absolute lowest point on a graph compared to all the other points that exist. And so you can see that I have 4 different pictures here sketched. I want to just look at each of these really quickly with you. You could picture that there would be arrows at the ends of all of these graphs, so we would assume that the graph would continue on forever, kind of in these directions. And so you can see in this first picture here, I have labeled that this peak and this valley are both considered to be absolute maximums because it kind of feels like the graph sort of levels out over here to the left and right, and there is no point on this graph that would ever be higher than this point here or lower than this point here. So here's an example of a graph that has both an absolute maximum and an absolute minimum. Okay, now as we look over here on the graph to the right, this is an example of a graph that only has an absolute minimum. There is no absolute maximum because we know that these arrows would extend up forever and the graph would just keep going up and up and up and up forever. So there is an absolute min, no absolute max. Okay, looking at the graph down here in the bottom left, now we can see that this point here would be considered to be an absolute maximum. There's not going to be any other points that are going to be higher than that. But there is no absolute minimum as these points are either just gradually still going down forever. Here, I think that's what the assumption is, that this is kind of carrying down forever. And then in this last graph, we can see that here's an example where there is neither an absolute max or absolute min, because we know that even though this is a relative max and this is a relative min, if we're talking about absolute, that graph goes all the way up forever and all the way down forever. There would be no absolute max or min. Now, here's what we're going to be doing on this one example here today, and then your assignment is just to do problems 1, 3, and 5 on, I believe it's page 225, okay? So what we're going to be doing is we're going to be doing this process where we're trying to figure out what is the absolute maximum and absolute minimum of a graph, but on a closed-in interval. And so I'm going to give you an example here. It's kind of the easiest way to sort of do this. Let's say that you have a graph that looks like this, okay? And I only want us to focus on, let's say, this interval right here. Okay, if you were to zoom in on your calculator to where I have this green box, ignoring the orange part of the graph that falls outside of that, I'm looking for, in this green box, what is the very highest point and what's the very lowest point. Okay, well, in this box, this right here feels like it would be the very lowest point. Where we need to be careful is sometimes we make the mistake for the highest point being the top of that hill, when in fact, there's a point in this green box that is higher than that point. It would be this point all the way over here, okay? And so we know that our critical values, when we were graphing by hand, we would take the first derivative, we would set it equal to 0, factor it, we would find our critical values, and usually it was at those critical values where we were able to identify a relative max or a relative min, okay? So our first step for these problems is going to be to take the derivative, set it equal to 0, factor, and come up with where those relative mins and relative maxes are. But in this example that I gave you here, you can see how this end point over here is actually higher than this relative max. Okay, so we would also need to just sort of figure out what are the largest and the smallest values on this closed-in interval. It could be our end points. This will become hopefully clear when we look at this one example here. Okay, so here's what we're going to do in this example. Okay, and the steps are along the side if that helps at all. Okay, we're starting right here with step number 1. Just a little notation here so that we're using kind of the same language. It says if the function is continuous, that means there's no gaps, it's all smooth and flowing here, on a closed interval, there should be an absolute min and an absolute max. Okay, if we're closing it off in a closed interval. We're going to call the endpoints of our interval EP, okay, the endpoints. And that's like kind of this part right here. We're only wanting to look at the graph between the x values of 0 and 3, even if the graph extends past that. So I'm going to guide you through these steps that you see along the right-hand side of your paper. I'm going to go ahead and label our first step here, number 1. And that step says, find the first derivative, critical values, by solving the first derivative set equal to 0. Okay, so what we will do, we're going to go ahead and take the first derivative here, pretty easy. We're just going to do the power rule. Okay, I'm then going to go ahead, set it equal to 0. I'm going to go ahead and pull a GCF out as I'm factoring here. Okay, now I have a trinomial. Okay, I'm looking for two numbers that are going to multiply to be multiply to be positive 5 and add to be negative 6. Okay, when I get those two numbers, I should be able to fill them immediately into my parentheses here. Those two numbers should be negative 5 and negative 1. So I'll put one here, the other one here. Now I have 3 factors, but technically only 2 of them that have an x in them. So my critical values are going to be x equals 5 and x equals 1. Okay. Now notice the other part to step 1. It says throw out any critical values that are not in the domain. Okay, the domain for this problem is defined up here. They only want us to pay attention to the graph between the x values of 0 and 3. So it's kind of like back here when I drew my green box. That would be like if I drew it from here where 0 is to wherever we're saying, x is 1, 2, and then over here would be where x is 3. We're only concerned about the graph just between 0 and 3. So if any of your critical values are outside of that domain interval, we're going to throw those numbers out. So 5 is not between 0 and 3. We're going to toss that out. The only critical value we're interested in is where x equals 1. Okay, that brings us down here to step number 2. Okay, step number 2 says identify the EV, which are the end values. The end values are simply the x values that are the ends of your domain. That's where x is 0 and that's where x is 3. I'm getting those right from up here where it's defining the domain for this problem. Okay, so here's what we know. We could have the highest point, the lowest point, could be where x is 1, or it could be cut off on the edges of the screen where x is 0 or 3, similar to what you saw happen up here where we said that this point over here is technically higher than what that relative max is. So we always want to account for the end values as well. Okay, this brings us down to step number 3. Okay, step number 3 is going to be where we're going to find the critical points and the end points by substituting our critical values and our end values into the original function. Okay. So we're going to take each of these, x equals 1, x equals 0, and x equals 3, and we're going to substitute each of those into the original function. This is going to give us our points. Okay, these are the three places where we want to compare which one is the highest and which one is the lowest. These get plugged back into the original. Plug into the original. Okay, so I'm going to plug 1 all the way up here into the original. I get a 7 back out. I'm going to plug a 0 in, I get 0 back out, and I plug 3 in, I get negative 9 back out. Okay, I'm going to look at these three values here, and it says in step 4, identify of those three which one would be the lowest, the absolute min, and which one would be the highest, the absolute max. So when you're comparing these, what you're looking at is you're comparing the y values. So the highest value is 7, so that is the absolute max point on the interval from 0 to 3. And the negative 9 is the lowest, so that's my absolute minimum on the interval from 0 to 3. So I think I have boxes down here at the bottom. We can write these in. I know this problem, I don't know if it asked us to graph this or not, but we're not doing any graphing by hand here. So it just wants you to identify, okay, the absolute highest point on the interval from 0 to 3 is 1, 7, and the absolute lowest point on the interval from 0 to 3 is 3, negative 9, which would have been one of the points at the very edge of your graph there. Okay, so this is basically what you're going to do for the three problems here on page 225, problem 1, 3, and 5, is you're just going to flow through these 4 steps, and it's basically this process right here. Okay, if you have questions, just let me know. Your assignment is, just write it here, page 225, and you're going to do problems 1 through 5